We are then moving to the third presentation today. Um, that is going to be given by Nate Iverson and Allie Brady about plan now or pay later, which I think is a very good illustration of what the It's Money concept is all about. Sometimes there is no money to testing up front, but there's always money to pay later. And you're going to illustrate it by if you plan now, you don't have to pay later. So the floor is all yours, Nate.
Thank you. Yeah, I'm Nathan Iverson, Veit and Companies, Vice President of Foundations. Just give you a brief overview. We're a specialty contractor. So, and we're preparing this presentation. We took a contractor's view on how this information basically manifests itself on the project and on the project team, not just in the design, but also in the construction. And with me is...
This is Allie Brady, a project manager also in our foundations group.
So the general talk will be going over 5 case studies in the upper Midwest, where we do the majority of our work, illustrating how limited information will often lead to construction complications, as well as if more information was available, how maybe an optimized design or potential savings could have been capitalized on, or in some cases were squandered in projects because the information wasn't provided or wasn't obtained until too late in the project. We'll go over 5 projects in the upper Midwest, primarily geotechnical in nature, especially foundations as well as retention systems. Well, just to kind of start this process, we'll go over some information that we're typically looking for on a project. The first, more of a site information. We're looking, what was the site prior to its new intended use? So historic information. This is often real pertinent when it comes to existing structures or maybe obstructions or pre-existing conditions that were maybe not a geotechnical origin, but man-made. Access and easements. A lot of retention systems utilize tiebacks as other temporary or permanent needs. Having these clearly defined help in our design process or during construction, as well as make sure we don't cause complications later. Utilities, both future and past, especially in urban work. They're often our number one issue on a project, just because utility contractors often install them. They don't maybe give the best as-builts. We only have a rough idea where they're located, and some of these are potentially a hazard or have huge financial implications like fiber optic lines. And they will then require us to maybe completely redesign, let's say, a retention system in order to accommodate them. Particularly expensive when you're starting construction. Much better to get that information out front. Adjacent properties, mostly concerned with vibration monitoring, vibration sensitivity. Preconditioned surveys are helpful just to get a good understanding of what we might have to deal with when working near these buildings, as well as mitigate litigation issues later on, as well. And then right away, just knowing where we can operate. Often we can bring a bigger piece of equipment, or we limit it to a smaller piece of equipment. Then we'll go to more what the talk is about, is the geotechnical information. Primarily, we're given is basically a geotechnical report and some soil borings. Often read the report, but often the information we're relying upon are the borings provided. We're looking at the quantity, the depth, the location, and how they're pertinent to our work, and then what sort of test results or testing has been performed on site. We're lucky if we get CPTs. Typically it's an SPT, rarely gradations, but sometimes unconfined and compressive strengths. Often we just get a pocket penetrometer. Piezometric data, water tables are really important for retention systems as well as other site considerations. And then site contamination. Certain issues can occur when dealing with contaminated sites. We often move a lot of dirt off site as well, which can often be a very expensive add to a project to all of a sudden handle all the soils that are removed off site. all of a sudden are going to a landfill, or let's say a drilled shaft was selected. The spoils are now contaminated versus if you could have gone to a full displacement pile and would not have had to bring those contaminants to the surface. So the type of geotechnical information or the decisions we will make from that geotechnical information, on the engineering side, we often do function in as a design build, in which case then we will make decisions on which type of retention to utilize is most appropriate, most cost effective, which type of foundation might be the most cost effective or easy to install. Specifications, either we're reviewing them from the engineer that developed them or develop them ourselves based on the geotechnical information provided. If there's a concern of high water, we'll make sure the specifications include appropriate measures to deal with water and related concerns. On the contractor side, this information is used to select which equipment we bring to the job, what means and methods we use to install the foundation systems or the retention system, as well as preparing a schedule for the project, which often the specialty contractor or even the dirt earth excavation contractor, they're roughly the first people on the site. And if you start your project 2-3 weeks late because of delays during this phase of construction, the entire project is forced to deal with those added delays and thus incur additional costs. So all this geotechnical information is, I think everybody understands, has a lot of value, and we can see how this information will manifest itself on some of these projects when it's limited, or if there was an ample amount, how good decisions were made. So the 5 projects we'll be discussing today, case studies, are Southwest Light Rail. This is Green Line. It's in Minneapolis, Minnesota. As you can see, these projects are all in the upper Midwest where we do the majority of our work. Mayo Clinic in Rochester, Minnesota. This is the basically primary hospital location for the Mayo Clinic. It's basically a hospital mecca. It's definitely a destination location. So entire city blocks, all they are is continued hospital buildings for either operations, patient wings. So everything is very congested, and there's a lot of work in the area, making work fairly complicated in that city. Highway 53 bridge. This is basically a old abandoned mine pit that a bridge needed to be constructed over in northern Minnesota, just south of the Canadian border. University of Iowa. This is the Children's Hospital addition, right next to Kinnick Stadium on campus in Iowa City. And then Loring Park Apartments, basically a mid-rise 37-story apartment building in downtown Minneapolis.
Yes, so we'll start off with the Southwest Light Rail project. This is a project with an example of limited testing prior to construction, which ultimately impacted the cost and the schedule greatly. So this project is a new light rail transit going from Minneapolis west to the suburb of Eden Prairie, Minnesota. The work in focus here are 4 permanent retention walls. In total, they run about 2,000 linear feet with a total retained height up to 40 feet. By the end of the project, there were approximately 475 strand anchors installed, which were detailed by the owner to be double corrosion protected. And ultimately, Veit did design the anchors while the owner designed the wall. So provided to us during the bidding and design phases of the project were about 10 soil borings, property easements, and design parameters, such as trumpet diameter, bond stress, and non-bond length. Early on in the design phase, the restricted anchor lengths due to the tight easements were brought up to the owner by Veit as a concern. So in hopes to increase the bond stress, which would allow us to keep those anchors inside the property, Veit did install 3 test anchors and tested them to capacity. Unfortunately, the soils proved to have a lower bond stress than even provided in the specs. By this time, the beams had already been fabricated with trumpets, so the diameter of the anchor couldn't change. Due to the design of the wall, all anchors had to be installed into trumpets, so they didn't protrude out of the front face of the finished wall. So going back to the soil borings, as shown in the detail on the screen, the borings were performed on the rail alignment and not on the retention alignment, which was up to 20 feet away. So the elevations of these borings on that rail alignment and the location of our retention system didn't align, which ultimately didn't provide the soil stratum details that we needed. Ultimately, during construction of the variability of the soils that we did experience, the capacity of the anchors were greatly impacted. And so the easement restraint forced us to install approximately 80 additional anchors on this project. And since we did have to have that trumpet requirement, we did have to install internal whalers between the beams to keep that front face as designed. If additional testing was performed prior to the design phase, substantial costs and schedule impacts up to weeks and months could have been avoided by a redesign of the retention system. So moving to the next project, we have the Mayo Clinic. This project's located in Rochester, Minnesota on the main campus of the Mayo Clinic. On the left side of this picture, we have a new utility, pedestrian, and service tunnel being constructed for future expansion of the campus. And then on the right is the new loading dock building that will service all deliveries to the Mayo campus in the future. In total, these two sites totaled approximately 2,000 linear feet of retention, and retained heights were up to 30 feet at its deepest point. So Veit was a part of a design build contractor with two different general contractors on each of the projects. And during the initial bidding and design phases, some concerns from the owner were brought up due to the layout of the job. Underpinning of the adjacent buildings were required. Vibration and noise concerns, especially during the typical working hours. And access had to remain open for the existing loading dock, which would require trucks to access across our tunnel alignment where the cursor is currently pointed. And then support for over a dozen utility crossings were required. These were varying elevations and also varying locations along that tunnel and loading dock alignments. So all of these issues were taken into consideration during the design phase with the owner. So as a contractor, we are provided 4 soil borings, as-built drawings of the adjacent buildings, and as-built info for the existing and then future utilities. Rochester, Minnesota is known for its varying rock elevations. So having this limited information, only the 4 soil borings, was unfortunate at the bidding and design phases. So due to the layout of the site on a city street, we as a contractor could not perform any additional borings prior to construction. It was only once the project started and we shut the street down ultimately that we could do any additional testing. Also, due to the limited access, the general contractor of the tunnel work required the anchors to be installed into trumpets in the beams in lieu of external whalers. So when the rock elevation issues were encountered, which varied from 8 to 30 feet below grade, modifying the beams and trumpets on site costs substantial time and money. So shown on this drawing, the points in gray were the rock elevations that were encountered. And then the points in blue and orange were where we anticipated rock. So this is just one section of the tunnel that we encountered. But as you can see, there was substantial differences in that rock elevations, which ultimately cost time and money. So fortunately, though, on the loading dock side, there was room for more external whalers to be used. So we were able to shift those anchor elevations as needed for the appropriate soil conditions that we encountered on that right-hand side of the project. Unfortunately, there was some issues with the as-built drawings as well of the adjacent buildings. During excavation, it was found that the buildings were not constructed as shown on the plans, which ultimately we had to shut down the job, do complete redesigns of the retention systems in those areas. But fortunately, in today's world, it seems red lines and as-built drawings seem to be improving, but getting those marked up plans to the next contractor is required to ensure safety and accurate designs are being made for future construction and allowing costs and schedules to remain on budget.
Okay, the next project we'll highlight here is Highway 53 bridge. This bridge, as stated previously, is in nice, warm, balmy northern Minnesota, just south of the Canadian border. As you can see, a fine picture here. cold weather. It's one of the colder places in the continental 48. This project is a little complicated. As you can see in the back here, this is a existing mine. This is one of the largest open pit mines in the world. This has since been shut down and backfilled. This particular site, up to, I believe it's like 135 feet below current grade, was mined, and then blast rock was backfilled into this valley. The bridge needed to cross from the far side to the side on the inside, I guess, towards the picture here. And the foundation system would then have to bear on this blast rock. It was deemed inappropriate for bearing directly on a blast rock due to potential settlement. So a deep foundation system would have to be utilized. These conditions were extremely abnormal for typical foundations, particularly in Minnesota. So a test pile program was proposed. They selected a driven or a downhole hammer pile or a caisson as two potential methods. A downhole hammer pile, for lack of a better term, is basically a large diameter micropile, which case on this one, the test pile program consisted of 16-inch and 24-inch, and production pile was a 30-inch, essentially micropile. There was ample soils information provided with rock cores, roughly 14 soil borings with cores just for this particular alignment. At the time of test pile, the bridge alignment had not been finalized. They were looking at either a longer crossing or a shorter crossing, different bridge elevations. This particular elevation, the final one, was the shorter crossing with a bridge deck to surface of around 200 vertical feet. So it's a relatively high bridge. This schedule was very aggressive for both the design team and the construction team. So a CMGC method was utilized for contract, and the test pile program proved instrumental in order to reliably predict and come up with a schedule for the project, as the foundation system was deemed the most uncertain element for the project, as the pile type wasn't finalized and the difficulties with installing a foundation through this rock were definitely a concern. So drilled shaft construction was evaluated at time of the test pile and was deemed most likely an unlikely candidate due to the rock and advancement of casing through the overburden. 135 feet of blast rock with potential random obstructions with, let's say, old rail lines or mine debris would form very problematic for a large diameter drilled shaft. So the primary method selected was the downhole hammer, utilizing a 16-inch and a 24-inch downhole hammer for the test pile program. Working with the different vendors of differing bit systems, Veit came up with a proposal. Working with the design team, these piles were installed. They proved a very fast installation. The means and methods were vetted out, and the test pile program was able to prove a very high capacity in the rock. The test piles on this site actually did not yield the rock. The piles, when dynamically tested, actually bounced out of the ground. So to give you an idea that not much setup on these for side friction, but end bearing was as much as the pile could take. So this is an example of, good information allowed on the front end, allowed for a successfully constructed project. When this project went into actual construction, we were on time and completed within budget for this phase of work. Another interesting project we had worked on for also with complicated geotechnical information would be the University of Iowa project in Iowa City. This is a 30-foot excavation on one side and a 50-foot excavation on the other. A combination of H-beam and lagging drilled and dropped, as well as secant walls, was used for the excavation. The foundation system for both the future ramp and building were designed to be buried on drilled shafts. These drilled shafts would drill through the overburden and then bear into rock based on the geotechnical report. Basically, one diameter into competent rock was required in order to meet their bearing pressures they're looking for. This is a very busy site, as suggested earlier. It's on campus. Kinnick Stadium is to the right of the picture up above. And this is the infant wing of the University of Iowa Hospital. And these are all basically each room is a premature baby ward in a lot of these differing rooms, which means vibration and noise sensitivity was a very significant concern, meaning only drilled in methods were allowed, and dust and vibration were actively monitored. Information given. This is often something we'll see on many projects. The cost of cores are relatively expensive. So there were 25 soil borings, but only 10 cores. The cores were also relatively shallow. 10 to 15 foot rock cores were given. This became problematic as the geotechnical report, as well as the structural engineer, elected to go to deeper rock cores or rock sockets for the drilled shafts, which actually pushed the drilled shafts almost outside the extent of the cores in many locations, as well as the consideration where they required through weathered rock and then into competent rock. During construction, we actually left the depth of the borings, and thus leading to complications in the project. The first issue was that since relatively limited rock information was provided, relatively conservative rock strength analysis was used for the caisson design. Skin friction was 100% neglected in rock and soil, and these were designed as purely end bearing. The drilled shafts, when going into construction, as mentioned, during the excavation of the lower section and drilled shaft installation, around 65% into the project, one of the drilled shafts encountered roughly 15 feet of weathered rock, at which point the rock socket then extended 5 to 6 feet deeper per the diameter of the shaft, and coal was encountered. This coal seam was relatively intact, but was not taken into consideration for the foundation design. At this point, the job was stopped, and additional cores were performed across the entire site. Concern was brought up that all the previously constructed drilled shafts might no longer be deep enough or might have to take a capacity reduction. In order to alleviate those concerns, Veit recommended a bidirectional test be performed, as well as the additional cores. During the bidirectional test, it was proven that this rock did have plenty of capacity. We tested this particular test in recovery of 15% and RQD of 10%. It was essentially some of the worst rock on the site, and we came back with some very good values. Unfortunately, if this information would have been provided at the beginning of the job, this would have meant around a 35% reduction in deep foundation costs. But since 65% of the project had already been completed and reinforcing steel had already been procured for the job, the savings was relatively minor, with basically a 2 to 3 foot rock socket reduction. The last one we'll go over is Loring Park Apartments. This job was also in Minneapolis, Minnesota, as well. It's 37-story mid-rise, very aggressive schedule, winter construction, vibration sensitive, as the adjacent buildings are relatively old, and a deep foundation was needed due to soft sands at the surface. The original proposed retention system was drilled shafts with rock sockets due to bedrock concerns. The drilled shafts extended through the limestone cap in many locations and were bearing down in the softer sandstone below. During the review of this information, 27 soil borings were provided on site and 16 rock cores. This relatively is about a half a city block. It's a fair amount of rock core information, but the rock cores were relatively inconsistent, suggesting there was higher variability than the 16 borings were showing. Particularly, one of the borings showed a deleterious clay shaly clay layer inclusion inside the bedrock. With only one boring identifying it, nobody knew exactly to the extent of where this concern zone would be. This is one of the reasons why a lot of the drilled shafts were extending well through the limestone and down into the sandstone. So upon reviewing this information, Veit recommended a VE design, which included 13 additional rock cores be performed in the core and key areas across the site where rock information was limited, as well as some additional cores around the inclusion in order to delineate its extent. Also, Veit recommended a bidirectional test to prove out bearing pressures in the rock in order to use basically a higher bearing pressure in the bedrock, as well as obtain friction values for the drilled shaft. And then in order to mitigate some of the construction concerns and due to schedule, downhole hammers pile, again, a large diameter micro pile was recommended to eliminate some of the smaller drilled shafts. They're faster to install, more like 10 a day rather than 2 a day, and eventually could prove a higher bearing capacity once we did the bidirectional test. With all this information put together, we were able to provide a cheaper solution, as well as a reliable schedule and an overall cost-effective savings for the owner and a schedule savings for the design team. Again, it's an example of how good information upfront allowed for savings and schedule return later in the project. So in conclusion, if you don't pay for it upfront, most likely you're going to pay for it in the end, and potentially more, as there's a very large snowball effect, as waiting for one, additional soil borings later shuts down the entire project. Or if the contractor brings a certain piece of equipment to the job that can't do it, now there's additional mobilization expenses to bring the pieces of equipment that are necessary. So this poor information, it was kind of showed in a lot of these examples, poor information leads to conservative designs, improper means and methods selected by the contractor or by the design team, construction schedule delays, which have compounding cost effects for the overall project, lost cost saving opportunities. This information, if obtained early on many of these cases, would have had savings or at least reduced costs for the project, as well as more reliable for the owners. Redesign. Definitely redesign in the middle of a project is stressful and often inefficient, and often shuts down the job. And then overall, all these things mean to just increase construction costs, which is ultimately why we could argue that getting this information up front, paying a few extra dollars for some soil borings, will definitely save the project in the end. I'd like to thank some key partners on these jobs: Minnesota Department of Transportation, Mayo Clinics, Met Council, University of Iowa, Brown Intertech, AET, and Dan Brown. These partners have all been instrumental in a lot of these projects to help look at additional information, and then illustrate how geotechnical information is definitely a valuable asset for a project. So I'll pass that over to you, Gerald.
Thanks, Nate, and thanks, Allie, for a very interesting presentation that really showcases the theme of this webinar series.